Hello, this is David from the package stage, and in today's video, we are going to walk through the virtual registries features. Um, Now, some expectations to set. This video will go through technical aspects of the virtual registries, as it is like a virtual registry quick onboarding video. And so I do expect the audience will know the GitLab code base and its different concepts like services, finders, and grep APIs. So this is not really meant for users of the virtual registries. Before diving on in the virtual registries, let's talk about artifacts registries. So you probably heard about some artifact registries, um, for example, packages registries like npm, Maven, or PyAPI. Um, in those registries, if we simplify them and simplify what they are doing, what happens is that you do have a um, project, or better said, a file that will describe a set of dependencies. And so there is a specific client, which is the dependencies manager client, that will pull those dependencies from artifact registries. So, for example, on npm, you can have an npm project that will list all the npm packages that you need in order to run this project. And so then you have the uh, manager client, which is called, yeah, npm. That's the official one. You do have other ones like yarn, but well, anyway. And so that client will pull the packages from different sources, which can be the official public sources like the npm registry for npm. It can also be from private sources or private registries. Let's have a look at the here at how this interaction with the clients and the registry happens. So in to do this, I'm taking as an example the GitLab npm registry. So um, this is basically a feature that implements the npm registry uh, protocol or interactions or all the endpoints so that the clients such as npm or yarn can pull files from there. So usually this communication will happen over http. It's usually it's a http api, a rest api. But it depends on the formats. Some formats can use other protocols, such as, well, Git, for example. But most of the time, it's a HTTP API. And so what happens is that you have endpoints to, well, obviously download the files. So basically, clients will send, hey, I need this package name, this version, and this file. So send it to me. There will also the client has also the ability to upload a package, so upload a file, because some dependencies are private, and you do have projects that will create a specific dependency and then publish that dependency to a registry. So you need an endpoint that will accept an upload. So you have both directions in a sense. And then we do have metadata endpoints most of the time. Metadata endpoints, um, it's the endpoints that will describe the state of the registry. So let's see what it is for npm. So basically, given a package name, this will return the list of all available versions of this package. There are other informations too, but let's simplify things. these metadata endpoints, they can be very, very different because it really depends how the format defines uh, the the expectation of the response from the metadata endpoints. So you could have specific metadata for a specific package and version. You can have general metadata like we have here for for a given package name. You can have a even more complex metadata where you have the entire state of the registry described, which means that all packages, all names, all versions, and all files that each version contains. So that's a huge response or document. You can also have formats that will not have a metadata endpoint. Instead, what they will do is they will pull a very, very specific file that is the metadata file, if you want. And so that file contains the description of the package registry. And yeah, that's about it for artifact registries. Another thing to know is that, well, the endpoints and how they are organized and same thing with the metadata endpoints, they are very specific to each format. So it's not like, okay, NPM clients, we use this set of APIs, and Maven clients, we use the same set. No, every format will have its own world of API endpoints and its own way to authenticate in those endpoints. So how the credentials are passed from the clients to the backend is very specific to every format. Um, so now you can imagine that you can have a project with different dependencies, some private, some public. And so because there is this mix, you can end up with having multiple registries defined, like the official public registry, and then one private registry for a specific private dependency, and another private registry for a very specific dependency. And you can end up with a pretty large amount of registry URLs. And for private registries, you end up with managing a large set of credentials because each private registry, since it's private, you need some credentials to access it. And so virtual registries is an answer to aggregate all of this. So how we are going to do that? Um, Basically, the virtual registry is a pull-through cache, and it acts as a proxy between the uh, artifact manager client and the actual registry. So in the GitLab instance is in between. What happens is that the client will access the virtual registry and pull files. And from a client point of view, I'm accessing a regular registry and I'm just pulling files. But behind the scenes in GitLab, what we have is that we have a set of what we call upstreams, because usually those are registries that are outside the GitLab instance. So those are remote upstreams. And we have a list of them. So when a file is requested, we go through the list of upstreams, try to locate the file where it is. And then once we find it, we pull the file and we return it to the client. So with this configuration, now your project doesn't need a large amount of URLs, credentials, and anything. You just need to have one registry, which is the virtual registry, and one set of credentials. While doing so, while being uh, acting as a proxy and seeing all the files going through, what we are going to do is cache them. So caching is another important aspect of virtual registries. So the goal here is that uh, when we pull a file and the cache is empty, so we inspect all the remote upstreams, get the file, and return it to the client. But while doing so, we are going to also to cache the file in the GitLab instance. This way, the next time the exact same file is requested, we don't need to contact the upstreams anymore, which is a costly operation, right? It's a network call because all these are remote upstreams. So instead, we can return the file from the cache. Um, this provides um, well a, a closer location of files. It can provide a closer location. You can imagine that in a CI job, if you try to build a project and you pull dependencies from a virtual registry and all the dependencies are present in the cache, then the virtual registry will serve those dependencies from object storage from GitLab. So all of this happens within the GitLab infrastructure versus if you have um, list of um, registries, registries, and you need to contact them. So suddenly your CI job needs to pull files from outside. The other thing is also reliability in the sense that, well, an upstream can have, well, reliability issues. And so if a file is requested and we have it in the cache, then we can serve it from the cache, even if the upstream is completely down. Um, that helps with situations where, for example, let's say that a public registry has reliability issues and, well, he's not having a great day. This can lead to um, pipelines failing because you can't build the dependency or you can't build the project anymore. And, and a virtual registry with all the dependencies in the cache can provide that, a protection against that situation. Um, last thing that we have is that because we have a single point where all the files, all the dependencies go through, this gives us the opportunity to have some validation or some tests on the dependency that goes through. So um, you can imagine, for example, that if a known package has a very severe vulnerability, as an administrator of the virtual registry, you might want to make sure that this package or this version is never pulled through the registry. So that's one thing that we could do. Okay, so now we are going to uh, deep to dive deeper in the technical concepts. So virtual registries. First of all, um, at the everything I'm going to describe here is at the time of this recording. So first thing is that we only work with the download operation. We only pull files from virtual registries. We never publish files to virtual registries. Uh, that might happen in the future, but for now it's only downloading. The other thing, the general design is that we do have different formats. Currently, we are working on NPM, Maven, and container images. Other formats will follow. But the general design is that because each format has its own set of rules and set of endpoints, right? We are going to store the data specifically for that format, which means that, for example, we do have virtual registries tables, plural, because we do have the Maven virtual registries table, we do have the NPM virtual registries table, and we do have the container images virtual registries table. We don't store everything in a single table because these can quickly snowball into, well, yeah, amount of data issues because we can be uh, we can be pulling a lot of files through virtual registries, and that creates a lot of data on the backend side. So this data is already split in the format where it's used. But that doesn't mean that on the code side, on the Rails side, everything is completely separated. Um, what we are going to do is that we are going to try to use the same concepts so that it's the same models or very, very similar models. And then we have ways to centralize the logic. Um, that would be that is the ideal goal. Um, so yeah, again, it's split on the database side, but on the Rails side, well, models are split. The actual active record models connected to tables, they are split, but we are going to try to centralize as much as possible. On the feature itself, it works at the top level group. So it's not connected to a project or a subgroup. It's always a top level group. The other thing is that this is an EE only feature, so you do need a Premium Plus license to use it. So it's EE only, and um, we don't allow anonymous users. So all users need to be authenticated. So you can't access a virtual registry without credentials. That's not possible. You need credentials. So we do have the top level group. Then I'm simplifying things here, but those concepts that we are going to walk through here, they are the same in NPM, Maven, and container virtual registry. So we do have the top level group. We do have the registry object. So here we do have has many relationship. However, we do have a limit. I think it's 20. Might be could be wrong, but there is a limit, meaning that you can't have an unlimited amount of virtual registries for a given top level group. That's what we have. Then we do have what we call the upstream. So there is right now it's remote upstream. So we do have URL, the URL to contact the upstream, and some form of credentials. So let's put username, password. Uh, and then here we do have a relationship with a cache entry. So a cache entry is actually the model that will store the object storage key for the file on object storage. So it's really, yeah, a record in the cache system. That's the thing. That's the thing. Um, yeah, what else? You can see that I didn't fill here between the registry and the upstream um, relation. And that's because upstreams are shareable between registries within the same top level group, meaning that you could have um, registry A that is linked to upstream 1 and registry B linked to upstream 1 2. Why do we have this? The reason is that the upstream object here can be pointed to the public registry, and usually the projects and whatever build system you use, they will need some packages or artifacts from the public registry. And so the goal is to avoid users creating multiple upstreams here that would point to the public registry and then pull common files or very uh, yeah, common files or common packages, and they will be creating multiple cache entries for the exact same file. So the goal is to deduplicate the the cached file across all the registries for the same top level group. So the scope is really the top level group. So between two top level groups, we can have the same upstream pointing, well, the upstream pointing to the same remote upstream and pulling the same files. But because there are two different top level groups, we are going to cache them in two different locations. So because we do have shareable upstreams, we can't simply link the registry and the upstream together. We need a join model. And yeah, after many hours of research, I came up with this name, registry upstream. So this one is also limited, and this one will have a one-to-one. Because this is a join model, so this is a registry ID and an upstream ID. It will also have a position. So why do we need a position? As I said, the virtual registry here is connected to an amount of upstreams, so up to 20 upstreams, but it's not a set. It's a ordered list. This is pretty important. The upstreams, they have a priority when we receive a request for a file. We are not going to like ping all the upstreams and like whichever upstream has the file wins. No, they have a priority. So if the first upstream has the file and the third upstream has the file of the first upstream is used, not the one from the third upstream. That's a very important concept. Um, And so when we walk the list of upstreams, there is actually an order of how you walk the list of upstreams. It's not a set, it's not random. So that's why the position is important. And it is at the registry upstream model, at the joint model, because an upstream can be shared between different registries, but they could be appearing at different positions, right? For example, the public, one recommendation that we have is that if you have an upstream for the public registry of your format, like npm registry for npm, put that upstream as the last one of your list, because you do want to check all the private dependencies first, and then you check the public ones. But between two registries, you can have a list that has a different size. And so put the upstream at the end of the list can mean different positions. So that's basically the design of all the models. But again, as I said, on the database side, they are specific for each format, meaning that, for example, upstream, you will have a Maven upstream table and an NPM upstream table. However, the models will try to work in a similar way so that we have ways to centralize the logic. Um, yeah, I'd like to go through the download flow. So the download flow is basically we need to check the cache, and then we have a giant if, right? So what we do is that we receive a request. Let's say request. Ah, wow. Okay. So first thing is check the cache. So here we can do that because the registry is the object that is pointed by the URL that clients will configure, meaning that when you have for example, npm, and you configure, hey, if you want to pull npm packages, pull it from here. That here is the GitLab URL to pointing to a virtual registry, well, an npm virtual registry. So we do have the registry. That's our entry point, if you want, when we download the file. So what we are going to do is check the cache. So we can navigate all the structure and just check the cache entry, because here we do have relative path. So we navigate this entire structure and check here if we do have a cache entry for this uh, this request. And then we have basically two two ways, two answers. There is a yes, and there is a no. Let's start with the simplest one. Yes. Okay, that's cool. So in this case, we can just take the file from object storage and return that file. So return file from object storage. If it's a no, we need to walk the list of upstreams. So in this case, we are going to take the list, the ordered list, and walk it. So we do have a service. Uh, yeah, the check service. So it's the one that will check if an upstream has a specific file, yes or no. And it will go through the all the remote upstreams to check if a file exists. And then we do have again two answers. File found in upstream, file not found at all. So in this case, well, uh, we return that, hey, we don't know this file because we checked all the upstreams and no file was found. File found in upstream. This one is where the position comes into play because it is found, but it depends on if it is the actual result that you want to use. So you can imagine the upstreams as a table of Boolean values, and the Boolean means if the file exists on the upstream or not. And so let's say that we don't know this one yet, we don't know this one yet, we don't know this one yet. We do know that this one has the file, we don't know this one doesn't have it, and this one has it. This is not a complete result because this list, again, is an ordered list and it's a priority. So if we don't know if those um, three first upstreams has the file or not, we don't know for sure if we can use this one. What we need to wait is for this result. And this way we know that, okay, so upstream number 4 on position 4 is the one that we want to use. So this logic of checking all the upstreams and waiting to have a complete result is what we have in the check service. It's upstreams, yeah, upstreams check service. Um, so now we know that this upstream has has the requested file. Um, what we need to do here at this point, we need to pull the file from the upstream, return it to the client, and we need to create the cache entry right here, this model, because we are in the, no, it's not in the cache case. So to do this, we are using workhorse. Workhorse has an instruction that is called send dependency. Is it correct? Dependency. Uh, I'm pretty sure that it's send dependency. Oh yeah, but then it's yeah the actual file that implements this is um, dependency proxy.go, but it's send dependency. If we look at the workers RB here, we do have def send dependency. Here it is. So this sends an instruction to workers to do something that is pretty smart and it's highly efficient. What it will do is that it will pull the file from the upstream. So in the send dependency instruction, we are going to use the URL on the upstream, then use the relative path, and then use the credentials, if any, to create all the information that workers needs to pull the file from that upstream. And so it will pull the file and it will install a T logic. So it will stream the file from the upstream. And as an output, we have two outputs because it will T the output. One of the output is the final client. So the final client, which is the artifact manager client, will receive the file from the upstream. It's an entire stream. And the other output is the upload. So what happens is that the virtual registry has a upload endpoint, but it's only usable by workers. So um, workers will identify itself to that upload endpoint, and it will send the output that is coming from the upstream to that upload endpoint. And so what you have is pretty smart, which is an entire stream from the remote upstream. We stream the file and we simply like fork that stream, and one of the output goes to the client, the other output goes to the Rails upload endpoint, and that endpoint is the endpoint that will create the cache entry. uh, of course, creating a cache entry, we need to make sure that we have only one, right? We don't want to store the file twice or three times for the username for the upstream. So we do have unique constraints, and we do have some logic around making sure that we store the cache entry only once. So once this is done, um, then it's all good. The client received the file, and the file is in the cache. So you have, yeah, in 4 lines, the entire logic of virtual registries. Of course, it gets more complex than just those 4 lines, but that's the main um, overall logic. And this is used for all formats like Maven, NPM, container. They will all work in the similar way. That's actually why, if you look at the check service, it's located in virtual registries upstreams, and you don't see any format because checking an upstream can be generalized no matter which format you are dealing with, right? This service can work across any um, model class of upstreams, as long as the class provides a way to, hey, here is the URL and here are the headers for the credentials. Okay, so we are good to contact the upstream. So this doesn't depend on the format, right? It can be generalized. And that's where you can see we do have a split organization on the database, but on the race side, we are making sure that we centralize things. Now, on this centralized aspect, it's not always true, as we are implementing the 3 formats at the same time, more or less. Right now, we do have some kind of duplication between the logics, but at some point, we will need to like move up or centralize or refactor, whatever you want to call it, things together so that only only one logic is declared once, right? Um, do I have an example? Yeah, for example, yeah, when you delete an upstream, deleting an upstream is not as easy as just removing the record. Why? Because there is a position. There is a position that needs to be updated, right? Because if you have upstream 1, 2, 3, and you delete upstream 2, then upstream 3, its position needs to go from 3 to 2. And so this is handled by a logic that can be centralized because this join model will exist in all formats, and the upstream deleting an upstream is not something that is specific to a format. Right now, I think that logic is duplicated between Maven, NPM, and container, but there is no reason to have that duplication, right? We could centralize this. So usually what we do is that we do have technical depth issues where we list all the things and all the duplications. And at some point, we will refactor to centralize things properly. Um, and that's about it for the entire flow of virtual registries. We do have additional things, but I will let you discover them in exploring the code base. For example, we do have lifecycle policies for cache entries. So basically, users can say, okay, if a cache entry is not used in the last, I don't know, like 6 months, well, we can remove it. Um, why this is important? Because cache entries are files on object storage, and files on object storage is an object storage usage, and that usage counts towards the overall object storage usage for the top level group. So the lifecycle tools are important tools to manage properly the object storage usage. As for the ongoing features that we are currently implementing, um, yeah, so the lifecycle policies are ones that are almost done. The other one is the allow deny filters. So that's the thing I said when you do have a single point and you pull all the artifacts through that point, you have the ability or the opportunity to run some filters so that you can quickly decide if, okay, is this file allowed to go through or not? And that's the allow denied filters where users can would have the ability to say, okay, I don't know, like this package is known to be uh, not great or bad. I don't want this package to be to be pulled through this virtual registry. So we can have a filter that will exclude that package, no matter if it exists or not from on the list of upstreams. The other thing that we are working on is the concept of local upstreams. So right now, this is a remote upstream. It's an upstream that is located outside. It's a registry that is located outside the GitLab instance. But GitLab itself has the package registry feature and the container registry feature, meaning that you can host artifacts in the GitLab instance. And so local upstreams are the ability to point to have an upstream that would be pointing to, hey, on in this project, because like in simple terms, for example, package registries, they work at the project level. So you host your private packages on a given project. So the local upstream will have the project reference, and it will act as a source of dependencies by looking at the packages that are available in under that project. And that's the local upstreams. And um, this is a pretty deep change because it it changes things for the cache system. You don't need a cache entry anymore because you don't need to store that file on object storage, because that file comes from a package that lives in a project in the same GitLab instance. So why would you store that file twice? No, what you do is you just reuse the object storage files that the object storage file that is pointed by the package file in the GitLab package registry. That's what we are going to do. And so this is the two features that we are working on: the allow deny list and the local upstreams. There are probably other aspects that we have, but feel free to explore. All the virtual registries codes lived under the same root namespace, which is virtual registries, and everything below is what we have for the virtual registries, whether it's services, models, APIs, same thing. It's always under the virtual registries namespace. This is quite important, and yeah, like we don't want to have the code in many different top level or root namespaces. It's only one. It's virtual registries. That's it. Then within the virtual registries, for example, we can check the Maven upstream. Where are you? Here. You see, we have virtual registries, packages, Maven upstream. As I said, this is the active record model for the table. This is the Maven upstream table. And as I said, we are using a dedicated namespace for the format, but that doesn't mean that we can't centralize command logic. Okay, that's it for what I have today. If you have any questions, anything, feel free to reach out, ping me on Slack, and we can have a look. And that's it for me today. Have a great rest of your day. Bye.